Hey everybody, this is Nick Losi and Caleb Unger, and this is part 2 of simulation for ENGI 460. And so if you remember in our last video, we talked a little bit about simulation, the differences between discrete, continuous, and Monte Carlo simulation. So in this video, we're going to be talking about more of Monte Carlo, what that looks like to evaluate an integral, how Monte Carlo uses integral estimation, and as well we're going to give an example and go through that a little bit in MATLAB. Before going into Monte Carlo integral estimation, let's give a refresher on evaluating integrals. So essentially, when evaluating integrals, we're determining the area that lies underneath a curve. So given a function that represents how a system changes over time or with certain constraint changes, a distribution may be developed. And the integral of a one-dimensional function can be described by this function on the screen, this equation. Monte Carlo simulation and integration allows for us to evaluate both simple and complex integrals. Utilizing random number theory, when we generate these random numbers, we can evaluate these integrals numerically. So as functions become more challenging to integrate analytically, Monte Carlo is a better option. The expectation of the integral can be evaluated statistically to estimate the approximated mean of the function. So now when looking at evaluating integrals using Monte Carlo, we have to have an understanding of the central limit theorem, which states that when random variables are added, their properly normalized sum tends toward a normal distribution. And what this means in Monte Carlo simulation is that when random numbers are generated, we can trust that they'll be evenly distributed. So to break down some of the different steps in the basic idea of Monte Carlo integration, first we want to draw the function of desired evaluation. So we do this across a specific area. Then we plot random points across this area on the XY plane, knowing that it will truly be random. And additionally, we want to count the points that are both falling above and below the function. And we can get an estimated area of the function by multiplying the total plot area times the points that fall under the f of x function divided by the total number of points plotted.
So what do we mean by Monte Carlo as an integral estimation? Well, as a foundation, Monte Carlo is the estimate of a sum of values over many iterations, which is also, like Nick just said, the area under the curve. This comes from generating random values over a given function and finding the area under the curve. So our first question then is, we can estimate the value of any integrand no matter how complex the integrand is. Why is that important? Well, this is important because when analytical approaches are not possible, you can use numerical approaches to solve complex problems. These complex and stochastic problems based off of randomness are very complicated to solve, and previously they were known as impossible problems, but now we can solve them using Monte Carlo and simulation. The simplicity of evaluation ranges from these complex problems even to simple integrals that you could solve analytically, just because the system of generating random iterations over the specific function or random variable of interest is the same process across the board. Therefore, Monte Carlo is extremely useful for these complex systems. So what relationships do integrations, probability densities, and fissionable materials have in common? It's a pretty crazy question, but if we look at it, the probability density is the integral of the probability mass function over a given set of values, over a range per se. So in taking the integral of the PMF, we find the PDF, or the probability density. We also know that fissionable materials have complex probability functions or probabilities for the likelihood of nuclear fission occurring based off of the speed and energy level of a neutron hitting the nuclide in the center of the nucleus. So with this, we can determine the probabilities over a given interval or range of values for high-speed neutrons for a certain material or certain nuclide that we're looking at. Therefore, the simulation or density of the fission occurrence happening, or the materials thereof that result, can be given using randomly generated variables and probabilities that such likelihoods would happen. Therefore, Monte Carlo can be useful for this application too. So question 3, how can I use Monte Carlo to solve a complex distribution function? Again, some of these functions cannot be solved analytically, and these distributions are new per se. They're not your standard normal distribution or your exponential distribution. It may be specific to your process that you're trying to map out. The reason we can do this is we can factor out a known distribution from this complex distribution that we have in front of us. If we can factor out a known distribution from the complex problem in front of us, then we can generate random variables based off that known distribution and run it through what's left over of the balanced complex distribution function, and again iterate over many iterations, plugging in the random variables that we're generating in order to obtain an expected value for that function. Graphing this, you'll be able to get the CDF, or the distribution function, and over these many iterations we can start to map out new distributions, which become very useful in the industry. So then, how are complex distribution functions related to the mathematics behind the determination of yields of fissionable and fusionable materials? Well, we know that they have varying probabilities based off of the energy amounts of neutrons, as well as what will happen to the atom after fission occurs. So Monte Carlo bridges this gap through simulation using the given probability functions or likelihoods that an atom will separate into two particular elements based off of a neutron hitting its nucleus. So we find out that the mathematics behind complex distribution functions is not able to be solved using analytical methods, but numerically simulated methods. Is that for the fissionable and fusionable materials, because the products and the occurrence likelihood for fission, for that matter, are random, and they are not set in stone. So we have to simulate the occurrences and the products over many likelihoods or iterations in order to determine our expectation for each, or the distribution of what could happen to that fissionable nuclide. Therefore, new distributions, including this one, of any complex system can be solved using Monte Carlo. So to close out, they were given a problem in the book to determine the optimal number of skips to hire for a certain business based off of a customer arrival rate and the probability that a skip is returned the next day or is still out on hire, and that was also determined from a binomial distribution. We were given the following on the slide to solve this problem. So to walk through the code, which we walked through in class, basically we're given a probability that the skip will return the same day if he is hired out, a lambda value, and the number of work days per year. So what we're doing is we're looping through the current number of skips and setting that equal to the total number of skips, and basically going through random iterations of generating how many skips are going to be hired the next day versus how many are not going to be on hire. to determine the maximum revenue for the given system, and from this we obtain a plot. The figure shows that the optimal number of skips to hire is 25. That concludes our video. Thank you for watching.